Hey, what's up everyone? Terry here, and we're going to go through this super common example in thermodynamics. It's to calculate the entropy change for an isothermal reversible expansion of an ideal gas, and we're going to derive the equation for it, as well as go through a super common practice problem as well. So let's get into it. So the change in entropy is delta S, and an isothermal process means that the temperature is constant there. So that's good, no problems here. Now we're expanding a gas. So if you imagine you have a gas here that's fitted with a piston in a container, and it's pushing on that piston, it's expanding. The molecules of the gas, they're performing work on the piston against the surroundings. They're pushing on the piston here. So normally the gas would get colder because it's losing energy in the form of work. The kinetic energy of the molecules is being transferred to do work against the surroundings. But in this case, the temperature is constant. So the energy lost as work from the molecules, from the system, is gained as heat from the surroundings. So there's no net change in energy within the system here. That means that the change in internal energy is going to be zero. Here. So for our first law, our du is 0 if we look at the infinitesimal form. So 0 equals dq plus dw, and dq equals negative dw here. Now we want the change in entropy, and the change in entropy we're going to get from the thermodynamic definition of entropy, or the Clausius definition of entropy here. So we'll plug in what dq is. So ds equals negative dw, and this is for a reversible process, over T here. Now what's dw? Well, this is pressure volume work that's going on. So the work dw is equal to negative pdv for pressure volume work. And because this is a reversible process, this pressure is the pressure of the system. If this was an irreversible process, then the pressure would be the external pressure here. Oh, and while I'm speaking about reversible process, I must mention this is an equal sign only because this is a reversible process. If this was an irreversible process, then there would be a greater than sign here, not equals to. So this is a hypothetical, idealized, reversible process. So we can have ds is directly straight up equal to dq over t here. Okay, so we'll plug this in here to our expression. Now we have two negatives here, so I don't want to lose a negative. So this is negative, and then dw is negative pdv over t. And these negatives cancel out. Temperature is constant, but the pressure is not constant. So as this gas expands, the molecules are moving with the same speed in a larger volume, which means there's less collisions with the edge of the container per given time than when they're really close together. So the pressure is going to decrease. The pressure is a function of the volume. And we need to express the pressure as the function of the volume. And we can do that using the equation of state for our ideal gas, PV equals nRT, where the pressure equals nRT over V. And we can literally sub that in. So I'm going to just rewrite that down here. ds equals, now the negatives are gone. P is nRT over V dV. Okay. Well, our temperature cancels out. And we're left with ds equals nR dV over V here. Okay, so to get the change in entropy, we need to integrate this from some initial, so the initial entropy to the final entropy, and then take the integral of the right-hand side from the initial volume to the final volume here. To evaluate this integral, it's not too bad. N and R are both constant because we're not injecting more gas or removing gas, so we're just left with the integral from V1 to V final of dV over V. And this is just the ln of V. So nR ln of V from V1 to V final, which is equal to nR ln V final minus ln V initial. And we can invoke a log law here to say that this is just nR. So there'd be a brackets here. Sorry, this is nR times ln of V final minus ln of V initial, which is ln of V final over V initial. I'll underline it here. This is the right-hand side, but on the left-hand side, this change in entropy, this is just S from S initial to S final. So that's just the final entropy minus the initial entropy, which is just our change in entropy here of the system. To combine this left-hand side, the right-hand side, this is just the change in entropy equals NR ln V final over V initial. There it is in all its glory, a reversible expansion for an ideal gas here. Okay, so that's our equation, and let's use it. So here's a common example that comes up all the time with this process, and it's to calculate delta S. Now this is the change in entropy of the system because there's no subscript here, so that implies that it's the system. The change in entropy of the surroundings and the total change in entropy when we have 1.4 grams of helium. So the mass equals 1.4 grams. This is helium. Okay, and the temperature is 298 Kelvin. And it expands isothermally, so temperature is constant, and reversibly from V1 is 0.50 decimeters to the final volume of 1.50 decimeters. We can calculate the change in entropy of the system directly because we just derived the equation for this. So delta S equals NR ln of V final over V initial, which is equal to, now we don't have the number of moles, we have the mass, but we can convert to moles because we know that this is helium. So 1.4 grams, and on the periodic table, 1 mole of helium weighs 4.0026 grams. The gas constant R is 8.3145 joules per mole Kelvin. You want to use the R with joules because entropy is often reported in joules or kilojoules per Kelvin. So this is the good one to use. And then ln of 1.50 decimeters, 1.50 decimeter cubed over V initial, 0.50 decimeter cubed. Okay, so 1.4 divided by 4.0026 times 8.3145 times ln of 1.5 divided by 0.5 equals 3.195. So 3.195 joules per Kelvin to 2 sig figs. What about the surrounding? Normally we would write the change in entropy of the surroundings based on the thermodynamic definition is equal to negative Q over the temperature. So the energy lost as heat to the surroundings is gained by heat of the system. But in this case, we didn't calculate what the Q is. But we do know that this is a reversible process. And for a reversible process, the change in entropy total of the system plus the surroundings is 0. And normally this would violate the second law of thermodynamics, but it doesn't because this is a hypothetical, idealized process. Reversible processes never really actually occur. So we can set this equal to 0 because this is just a hypothetical process. So if this is the case, then using the second law, the change in entropy total is equal to the change in entropy of the system plus the change in entropy of the surroundings. Now this is 0, and we have the change in entropy of the system. It's 3.195 joules per Kelvin, 2 sig figs, and we want the change in entropy of the surroundings. So we can just transpose this to the other side. It's literally the same number, but the negative of it. So the change in entropy of the surroundings is negative 3.195 to 2 sig figs joules per Kelvin. So negative 3.2 joules per Kelvin. Okay, there we go. So we got the change in entropy of the system, change in entropy of the surroundings, and then change in entropy total for this idealized reversible process. Hope you enjoyed it. Give it a like if you do, because that motivates me to make more videos. And I'll see you in the next one. We're going to do more calculations on entropy. By the end of this series, you'll be an entropy calculation warrior in thermodynamics. All right, cheers.